It is a common intuition that placing two stable objects close to one another will automatically form a functional connection. In the Unified Harmonic Systems framework, that intuition is a fallacy. Spatial proximity does not guarantee structural coupling. We define a true bridge as a mathematically verifiable, dynamically stable harmonic coupling between persistence-qualified cores. Admissibility is determined by the primary interaction energy equation. This serves as the absolute test for whether a candidate pairing qualifies as a structural edge. This expression filters coincidental geometry into three distinct requirements: base coupling, the coherence corridor, and phase parity. To understand how stable networks form, we have to build this mathematical contract from the ground up, term by term. Without passing this specific threshold, any proposed structural lattice is built on a foundation of ghosts. We begin with base coupling strength, which is derived from the product of the relative core amplitudes. However, amplitude alone is meaningless without accounting for spatial decay, as influence moves between these 2 points. This exponential decay term strictly limits the baseline strength of the connection across physical distance. This decay envelope defines the coherence corridor. The corridor is not a measurement of empty geometric space. The continuum between cores is an overlap background that acts as a medium, actively conditioning the coupling envelope. Depending on local conditions, this medium can prematurely filter weak structure into the ambient noise floor. This medium condition damping effectively shrinks the usable length of the coherence corridor. If the corridor collapses, the bridge claim is invalidated, regardless of the strength of the cores. Consequently, the true constraint on a network edge is not separation, but the survivability of the corridor through the local medium. The final hurdle for bridge admissibility is the phase constraint. This cosine term calculates the total instantaneous phase difference between the interacting modes. A bridge only survives if these modes reinforce each other under the same admissibility regime. This state of active reinforcement is called phase parity. We determine this difference over time using a secondary relation that accounts for frequency mismatches. Frequency detuning occurs when the bound frequencies of the two cores do not perfectly match. This mismatch causes the phase relation to drift continuously. Operationally, the bridge begins to alternate between attractive parity and destructive repulsion. Static spatial models cannot capture this. A bridge must maintain a reciprocal lock within a usable time window to prevent structural cancellation. We can test the long-run stability of a pairing by combining corridor decay with the oscillating requirements of the phase constraint. This graph plots interaction energy against spatial separation. As we pull the cores apart, the resulting energy does not decline in a straight line. Instead, the interaction fluctuates, creating a series of peaks and valleys across the corridor. Stability is localized at these specific minima points, where the phase relation rests at exactly 0 or pi. These windows represent the phenomenon of phase locking. This leads to a counterintuitive result. Slightly increasing the distance between two cores can restore a bridge from a broken state into a locked state. As a topological reality, stable bridges do not span all distances uniformly. Phase locking forces network motifs to cluster at discrete separation windows, prioritizing temporal alignment over mere proximity. Once a bridge passes the interaction energy test, we must classify how it responds to environmental stress. We calculate coupling stiffness by taking the second variation of the interaction energy. This defines our taxonomy, categorizing bridges as rigid or flexible and symmetric or asymmetric. A rigid bridge snaps back from perturbation, preserving its coupling class across wide stress ranges. A flexible bridge retains coupling but allows for larger drift, deforming without a total break. We also distinguish symmetric bridges, which behave identically in both directions, from asymmetric bridges, which show directional or contextual imbalance. Lattice modeling requires these specific tags. Assuming all bridges act uniformly would lead to incorrect predictions of network stability. In this framework, knowing a bridge exists is structurally incomplete until you can mathematically predict how it will deform. We can now apply these rules to a macroscopic environment of active, proximate cores. These filters reject the majority of candidate pairings, leaving only the connections that satisfy the strict requirements of phase parity and corridor survival. What remains are genuine, load-bearing lattice candidates. Finally, we address the limit case. What happens when the coherence corridor is effectively unbounded relative to the system scale? This is an entangled bridge. The manuscript defines this as a non-local correlation constraint only. The framework prohibits using entanglement to claim causal signaling or the transport of energy. By sanitizing our edges of proximity bias and unbounded transport claims, we establish the structural primitives required for the construction of robust lattices.